So we're going to calculate f prime of t, where we have that f of t is given by the following formula. So we have f of t is equal to t to the third minus 11t plus a 3. Okay, so let's calculate this. Alright, so if we want df dt, what we're going to have to do is this f here, we'll write in the formula, so t to the third minus 11t plus 3, and then so that replaces our f, that's like our f, and then we have a d dt. So we are differentiating or taking the first derivative once with respect to t. Okay, so let's break it up using our linearity rules. Okay, so this we could break up into 3 separate functions, right? And they're all connected by either a plus or a minus sign. So we could actually have d dt of t cubed, and then minus sign separates it from the next term, so d dt of 11t, and then plus d dt of 3. Okay? Alright, so now let's actually apply what we know. So for this first one, and the second one, and the third one, we can actually use the power rule, you know? So anyway, so here's our power. So we're going to bring that down in front, so we have a 3, and then we're going to write t to the third and subtract a 1 from the exponent. Okay? We'll do the same for the next one. Also, we have this added 11 there, so what we can do, according to the constant rule, or the constant linearity rule, we can bring that out in front, just pull that out there, and then we're left with d dt of t. Okay, we'll deal with that on the next step. And then here, what we have is a 3. Yes, so we have a 3. This is like a 3 times t to the 0, right? Because t to the 0 is just a 1. So we can consider it like that. So what we're going to do is bring the 3 out in front due to the constant rule for linearity, right? So 3 times d dt, and we'll leave that t to the 0 in there. We'll see what happens. Okay, so now we can simplify this, and we get 3 times t squared. Then we have a minus 11, and d dt of t, this is like a t to the 1, so we're going to bring down that 1, and then we'll have t times t to the 1 minus 1. And then over here, for this last time, we have a 3, and if we bring down this exponent for the coefficient, that would be a 0 times t to the 0 minus 1, and this whole term here is going to become a 0 because of this 0. Okay, so that's a 0, and now let's simplify this last part. So we have a 3t squared minus 11 times t to the 0, so that's just a 1. So 3t squared minus 11 is our f prime of t. Okay, so this is equal to f prime of t. Alright, so now what can we say, what is the first derivative? Like, what does it tell you about a graph? Okay, so what does first derivative tell you about the graph of f of x, let's say, okay? So let's say your given function is f of x, and what does it tell you about the graph of f of x? Okay, so here's what it does tell you. So if our f prime of x, sorry, you can't see the prime, f prime of x is positive at a certain point, then we know that the tangent line has a positive slope. Okay, so positive and positive. All right, but if f prime of x is conversely negative, then the tangent line, I'll abbreviate, tangent line has a negative slope at that given point. Okay, or on a given interval, whatever you're looking at. Okay, and then what about the magnitude? Like we just studied the sign. I told you if it's positive, the tangent line has positive slope. If the first derivative is negative, the tangent line has a negative slope. But what about like the magnitude of it? Like, what if you get a -2 versus a -5? What does that tell you? So the magnitude, or the so the magnitude of f prime of x tells you the steepness of the slope. The steepness. That was a really weird. Okay, so steepness. So how steep is the hill that we're going on, or traveling down or up? Okay. All right. So now we'll go over kind of a special case for derivatives. So a special case called e to the x. Okay, so this is the natural number e. Okay, so the natural e. This is e is a unique number. Okay, and it was actually found or formulated. Well, I guess it was found to be about 2.718, and it's called it's a natural number. And basically, the cool thing about it is that the derivative of our e to the x is simply e to the x. It doesn't change, all right? So that's kind of cool, right? So whenever you see an e to the x or anything like it, you're probably going to get something exactly like what you just had, or maybe a little something added in the front there, which we'll go over in our problems. Okay, one of the last things I want to go over is that differentiability. So this is going to be a long word. Brace yourselves. Differentiability. What does it do? It implies continuity. Okay, so this is true for basically all cases, and this means that you can't have jumps or holes. Can't have jumps or removable holes. Removable. I think I spelled that wrong, but I'm not sure. Removable holes. It's okay. This is not a spelling class. This is for math. So what that means is that basically let's say you had a function like this, and then it kind of like jumped up to here and kind of continued along, right? So what would you do here at C? Is it differentiable at C, or I don't know what's going on. So let's see what happens. Let's see. So here's the tangent line as we're moving across. As we get to this point, there's the tangent line, and here's the tangent line here, right? But the thing is, because there's no other side, because it doesn't continue right away and it jumps down here, you could have a tangent line like this. It would still go through the point, but we're not sure because there's no other side of the graph at this point. So we could have tangent lines. We can have an infinite number of tangent lines going on. See this? So the problem with when a function is not continuous, or when it's discontinuous for any reason, you can have an infinite number of tangent lines at this point C. So I'll just write it down. So there's no one or unique line that is tangent to the curve or our graph at x equals c. Okay, so that's a big problem there. So when something is differentiable, you can just basically assume, or that implies that it is continuous as well. Okay? All right, one last thing. Something to note is that you can have a continuous function. So what if you were to have a continuous function, but not differentiable? So differentiable. I'll abbreviate here. Okay, so an example of this would be if we were to have, let's say we have the absolute value graph. Absolute value, and then we moved it a little bit to the right. Okay, so here's our x and our y. What happens at this point? So let's say we're going along. Okay, so here's this point. Our tangent is actually, like, it mirrors the line, right? So we're going along, but what at this point, what happens? Like, we can have it continuing here, or it could also be here, right? Or it could be here, or it could be here, or it could have a, there are basically infinite options for a tangent line that you could have. And then as you continue along, you start going along the other line. But at this point here, this is the crucial point where it is continuous. There are no holes and no jumps or anything like that, but it happens to be not differentiable because this is a corner, it's called. So at a corner, it's not differentiable because you can have more than one tangent line there at that point. Okay, and another example that's not a corner, but this one will be called a cusp. So let's say you have a curve going along, right? This is continuous, right? So then, and you keep going. It's kind of like a wave, okay? So at each of these points, down here we have tangent lines leading up, okay, tangent lines. And also on the other side too, right? Tangent lines, that did not touch, okay, and tangent lines, etc., etc. But at this point here, what do we do? So can we continue this way? Or it could also be like that, or it could be like that, or like that, or like that. So this is called, the one I just showed you is called a cusp. This is not differentiable at this point here, point C, let's call it. And this, again, is a point C. So at a cusp, it's not differentiable, though the function might be continuous. And also here at a corner, you can have continuity but not differentiability. okay? Because there's more than one possible tangent line. All right, so that wraps it up for this video. I hope that helped, and good luck on your homework.